Hey, everybody. Welcome to the Compound Performance Group Mentorship. Today, we will be discussing physics, basic physics, leverage models, and some of the important stuff that goes on with this. So, one of the things that we need to go over, and we need to go over this before we can go over anything else in serious detail, is physics, because physics is going to dictate the way that everything is going to be happening in the human body and the way that the body is going to be responding to training. So that's an important thing to look at. And if we don't have a basic understanding of the stuff that we're going to be going over today, it will make it a lot harder to talk exercise selection, program design, and things of that nature. So let's get started. Uh, Again, like I just kind of reiterated and like I just said again, physics is going to be one of the most important things to take out of this entire program in regards to exercise selection. Everything we're doing is going to boil down to this, all of it, like everything possible. Exercise selection, fatigue, and load management. So how much work is happening in each area? How much load are you imparting on each tissues? Everything that we're going to do, tissue biasing, it all comes down to physics, and it's all going to be based on a perspective of physics. So we're going to start very simple, and we're going to think about gravity first, right? Gravity is going to be the only constant, and gravity is just going to be the applied pressure downwards towards the earth that the body is going to be resisting and fighting against at all times. For example, if we are just standing normally, our body is now doing our best to resist gravity and not allow us to just collapse and fall into a little pile of jelly on the floor. Conversely, if we are now standing up, we are fighting against gravity and moving against this constant force that's pushing down upon us. When we are lifting weights, what we'll be doing is we'll be adding an additional load to the force of gravity, but all of the loads and everything that we're going to be lifting are also still subject to the gravitational forces, which means that they will continuously be pushing down even as we are trying to do anything with them. No matter what position the bar is in, no matter where the bar is, no matter where the cable is, gravity is going to be pushing something down. So, in the example of a barbell or a dumbbell, it's pushing the load directly down to the floor, and you have to manipulate your body to target different tissues and use different things. With the example of being like a dumbbell bench press, where you're pressing the dumbbell from the bottom to the top to use the chest and use the pecs, versus a dumbbell row where you're pulling the dumbbell from the bottom to the top, where you're using your lats or your mid back depending on the path of the arms that you're using. This is just an example of how you have to manipulate your body to bias gravity in your favor to target the tissues that we're trying to target. With a cable, all you would end up doing is moving the cable or moving your body and manipulating your body around. So if I wanted to do something like a lat pull down, I would just lift the cable up really high and pull in a vertical pattern. If I wanted to do a low row, I would move it all the way down to the bottom and pull it up that direction. If I wanted to do a chest press or a fly, I would turn around and face the opposite direction and just move the cable in the way that I wanted it to go. The thing, what is going to be acting against gravity is going to be the pulleys and the weight stack. So the weight stack itself is going to be the thing where all the load is, and that's going to be the thing that gravity is fighting. And then we have a pulley system that allows us to kind of work around it and bias the movements into the path that we want to move them into. So this is going to affect training and loading, because we know that this is going to be just pushing straight down, right? So what we can use is we can use this in our favor to kind of look at what's going to be determined, what's going to be, what tissues are going to be used more in a particular exercise to see what tissues we're biasing. This is going to be very helpful for any kind of exercise selection or fatigue and load management when it comes down to those strategies, as we cover those later on in the program. So first thing we have to go over after we've gone over gravity is we're going to go over some levers, right? So levers are going to be something that we're using, and the model of leverage is something that we're using to determine how we are best fighting gravity and fighting load. So what you'll see is there are three classes to the lever system that we're looking at here. So what we've got here is we're going to have a class 1 lever here. We're going to have a class 2 lever here and a third class lever here, right? So class 1 lever is where the fulcrum is in between the load and the effort. So the fulcrum is also called the pivot or the axis of rotation. And if we look at this in the first class lever here, we have an equidistant distance between the effort arm and the load arm, which means that if we're putting 1 pound of load down, we also have to apply 1 pound of effort to maintain a neutral lever orientation. So to keep the lever right here, all we have to do is put 1 pound down and 1 pound down of effort. If we now apply 2 pounds of load, or put down 2 pounds of load and keep that same 1 pound of effort, this is going to drop the load arm and lift up the effort arm. If we then apply 4 pounds of effort and 2 pounds of load, the effort arm is going to move down, the load arm is going to move up. But if that's always staying at a 1-to-1 ratio, this is going to maintain balance, and this is not going to move at all. A good example here, an easy one that we can look at, is the skull on the cervical spine. That is pretty balanced, and we don't have to really worry about like applying effort to keep the head in the position that we want to keep the head in. A second class lever is where the fulcrum and the effort arm are on opposite sides, right? So we've got the fulcrum or the pivot here, and then as far away as humanly possible, we have the effort arm. And then in between those two is where the load is placed. So this would be like the example of a wheelbarrow, where you have the wheel here, the handles here, and all of the load going directly into the middle. With that, this is going to make it easier for you to lift a little bit of load. So as we put load down, you have to apply actually less effort to create the same movement. So if I were to put down a pound here, these are not going to be exact numbers, so just don't quote me on them exactly. There will not be a test on this, so don't worry. If we're putting down a pound here, we maybe only have to apply a half a pound of effort to lift this up, maybe even a quarter pound. It's nowhere near the same amount of effort that needs to be applied as the load here, right? So however heavy the load is, the effort that's being put in is going to have to be less to lift that lever up and have that point move closer to the pivot. A great example of this would be something like the ankle, where the effort would be the foot or the toes and the ball of the foot. The load would be the actual, like the front of the ankle and like the talus, and the pivot would be towards the calcaneus and the tibia and the fibia that go over the top. Moving finally to the third class lever, this is where we're going to have the effort and the load and the fulcrum relatively close together, and the load is going to be very far away from them, right? So this would be like a shovel, right? If we are looking at the fact here, this is going to be the handle of the shovel, this is going to be your hand, and this is going to be the blade of the shovel. So you dig it into the ground, and you have to use this hand to pull that load up and rotate it around the handle of the shovel. This is going to be one where we have to apply more effort than the load, right? So if there's 1 pound of load, we may have to apply 3 to 4 pounds of effort to create that same movement. And why are these going to be different? This is all going to come down to the length of the arms, right? So the longer lever, if you're looking at the effort arm being the longest portion, that's going to make things significantly easier to move because the load is closer to the pivot, which means that you're going to move this further than this part is going to move, right? So for the same distance, or for the same total distance, this is going to apply less effort than this one is. Whereas this one, this load is going to be moving the furthest, and the effort is actually going to be moving a shorter distance, even though it's going to cover the same total range of motion with the lever. So we have to apply more effort in the third class lever than we would in the second class lever, just because of the distance of the load and the effort arms. This would be something like a bicep, where if you're doing a bicep curl, the load would be in your hand, the effort arm would actually be the bicep attaching down into the radius, and the pivot point would be the elbow. So this is very close, this is very far away. It's not quite as advantaged as these two lever systems are. Now, if we're looking at the body is primarily composed of more third-class levers. There is a large difference between both internal and external leverage, and we're not going to really be covering those because we're going to keep this relatively basic. We may talk about those in more detail on the calls, but for now, this is what you guys have to know. Force curves are going to be another important thing because they're going to note with levers, because they're going to determine the loading ratio of static load, right? So when the load is very far away from the fulcrum, the load is at its heaviest. As the load moves closer to that fulcrum, the load is going to get lighter, or the felt load is going to get lighter. So if we have an example here, right, where I'm drawing a lever and I have this fulcrum point here, and I have a lever that extends out this way, as that lever moves further and further and further back towards the load where it's going to be stacked, this is where we're going to get to a point where the load is going to be decreasing over that curve, right? So as this curves back, the felt load is going to be getting lighter and lighter and lighter and lighter. As this drops down, the load is going to be feeling heavier and heavier and heavier and heavier and heavier, because this is going to be furthest away from this respective to gravity, right? So remember, if gravity is pushing directly down, out here, it has the most to overcome for gravity. But as it gets to about this point, it's overcoming a lot less gravity to fight that same distance or to move that remainder of the range of motion. So it's one of those things where if we're looking at this, it is an important thing to note, because if we're not aware of how this is going to move, we're not aware of what the force curves are going to be, right? So if we're looking at this, all free weights and machines are going to have force curves, right? If we're looking at this, free weights are going to almost always be heaviest where the body is the least advantaged. So if we're looking at this during like the example of a dumbbell bench, where the load is going to be furthest away from the body is going to be at the very bottom. It's kind of to the middle, right? That's where the load is furthest away from the body. And that's usually the hardest point for you to overcome. In something like a dumbbell row, it's going to be the exact opposite, where it's going to be heaviest down towards the very bottom and actually get a little bit easier as you get towards the top. If we're looking at machines, machines are also going to have a relative force curve depending on which kind you're using. If we're using something like a plate-loaded machine, those are definitely going to have a force curve. If we're using something like a cable or a pin selectorized machine, it's going to be a little bit more consistent throughout the remainder of the time. So if we're looking at this, if we're trying to feel what we're going to be feeling here, using something like a plate-loaded row machine would be the hardest at the very bottom and easier as you get it towards the top. Same with the plate-loaded chest press, right? If the pins are at the very bottom, as I go to press up and the pins get closer and the weight horns get closer towards stacked over the machine, it's going to be getting easier. If we're looking at something like a leg extension that's not plate-loaded is going to be relatively consistent for the entire time. Cables are going to be about the same too, because there's not a point where they're actually going to get harder, simply because the cable is the stack of weights is just moving vertically. It's just moving up and down, and the cable is actually moving around. So cables are not really going to have this. They're going to train more of the fullest and the mid-range of motion of tissues. Most machines, if we're looking at plate-loaded ones in particular, are going to have a force curve, but most regular machines are not really going to have one. They're going to train a little bit more consistently. So if we're looking at this, if we're going to turn this into some free weight motions and some free load motions, if we're looking at the squat, the bench, and the deadlift, right? The squat, the load is going to be the heaviest in the hole. And if we're looking at this, it's going to be the heaviest in the hole because the load, which is on the back, is going to be the furthest away from the hips and the knees, both of which are fulcrums. So if I'm going to draw and share my screen here, and I'm going to draw a little diagram for you guys. So if I'm here, right, and I am squatting, this is my knee joint, this is my hip joint, this is the barbell, right? If we're looking at this and we're looking at the bar being directly over midfoot, what we have here is we have a distance that's going to be set between the hips and the knees, right? This is going to be the area where both of these tissues are in their most lengthened states. We've got the most lengthened quads and the most lengthened hamstrings and glutes and spinal erectors. This is where the load is going to be the hardest, because the distance between the weight here, the imposed weight, which is this vertical dashed line, and the fulcrums is the furthest away. As we go to stand, so let's say we're standing up and we're here, right? So we've got that same person who's almost completed the rep. We've got that same line here. Look how much shorter the distance between the fulcrum the two fulcrums here are. That is significantly shorter. And what we're looking at here is as the body is getting more close to stacked, we're getting more close to neutral, where there's going to be just the force of gravity plus the load pushing down, but joints are stacked over each other. So there's very, very little actual work occurring, which is one of the reasons why when you see a lot of people fail a squat, they fail it either in the hole or just out of the hole, because this is where they are the most disadvantaged in terms of the movement. This is going to be the same thing for both a bench and a deadlift, right? If we're looking at a bench press, when the elbows begin to flare and push up off the chest, that is where the elbows are the farthest away, or where the fulcrums are the farthest away, which is going to be the elbows and the shoulders from the load, which means that is going to be the most difficult position there, which is why you see most people get stuck right as soon as their elbows begin to flare and as soon as their elbows get to about 90 degrees. In a deadlift, it's usually going to be the same, where if we're looking at a conventional or a trap bar deadlift, that's going to be the heaviest and pretty much the hardest off of the floor. And once it gets off the floor, it's going to be pretty close to done. And sumo is going to be relatively hard off the floor as well, just because we're looking at the knee joint in a way of pushing the knees in towards the middle and to adduct towards the midline as another moment arm. So to get the bar off the floor in a sumo, you need to both extend the knees and drive the hips up at the same time while adducting the femurs. So it's going to be a little bit harder off the floor than even a conventional would. With a conventional, you're going to be hardest off of the floor, or a trap bar, it's going to be hardest off the floor or getting it started, because the hips are the furthest away from that point. So if we're looking at the hips again here in a conventional deadlift, right, let's say we've got somebody here, right, we've got their foot. We've got the hips, which are going to be the furthest thing away from the load here if the barbell is in this spot here. So we've got this line here. This is going to be the furthest thing away. This has the furthest distance to move. This is going to be the hardest part of the movement, is getting this off the ground. And then as soon as that's done, as the hips start driving closer towards the bar, it's going to get easier and easier and easier, which is one of the reasons why you'll see a lot of people that'll fail a conventional deadlift or a trap bar deadlift between the floor and their knees, and a sumo deadlift, they'll either fail it on the very floor or at the very, very top. So if we're going to clear this out, I'm going to go back to here. Okay. So I think we've covered that one pretty well. So if we're looking at this, the axis of rotation is important, is an important thing to note, because if we're not looking at this, we are not looking at how we're going to be utilizing tissues in the way that we want, right? So this is what we're going to be looking at, right? If we're looking at training tissues and we're looking at using physics for exercise selection, what we're looking at is what is the furthest point away from the actual load itself. So if we're looking at the example of a front squat, while knees are going to travel significantly further forward in a front squat than they would in a back squat, the bar is also in front of the body. So this would still kind of have the bar bisect the femur in a way that would mean both the quads and the glutes are going to be working. Whereas with a high bar back squat and a bar it's a little bit on more posterior and a little bit more behind you, the knees are going to be driving a little bit far forward, especially if you're on a heel lift, which is going to allow the quads to work a little bit more. Now, when we're looking at this, what we're going to try to figure out is how we're using these tissues in a way to determine frequency, recovery, and training intensity. So if we're looking at these and we're looking at the movements that we're selecting, if you are selecting barbell back squats or like low bar back squats, and that person's got a very hingy squat where their hips are moving and their hips are going through a greater joint excursion than their quads and their knees, and they're also doing a conventional deadlift, we now know that they're basically hinging and deadlifting twice. So what we would probably do is figure out a different way to get them to use their quads a little bit more effectively by giving them a leg press or a hack squat or something that is going to bias the joint that's moving through the greatest range of motion to be the knees, right? If we're looking at this again, if we're trying to determine optimal training frequency, this will also help us with session placement. Because if we're looking at a remote client who just moves, who's got like proportions that are not really well built for any particular movement, for like a squat or a deadlift or any of the ones that we're looking at training them in, we can very easily determine where to put them. Because if they're squatting on Monday and their squat is very, very, very hip dominant, and then they're deadlifting on Tuesday, we know that their deadlift is probably not going to be the strongest one. So that one should probably be a lower intensity deadlift. Whereas if they were to be deadlifting or squatting with a bit more of a high bar position and deadlifting with a very, very like hingy conventional deadlift, we may be able to do those two back to back because we're training different tissues, right? We're also going to be looking at what positions are you training the tissues in. So where is this going to be the hardest, and where is the exercise going to be the hardest itself in the exercise selection that we're using? So in that example of a squat or a deadlift, we're training the lengthened position of the quads or the glutes or the hamstrings. So if we're only training the lengthened positions and we're not training the shortened or the mid-range position, we might be potentially leaving gains on the table. So we might have to find and choose some exercises where the load is going to be hardest when the movements, when the muscle groups that we're targeting are the shortest. For example, banded leg presses or reverse banded leg presses or leg extensions or leg curls or hip banded RDLs or 45-degree glute extensions, things like that, that may be able to give us the ability to train the shortened and mid-range of those tissues. This should help us very easily keep a little bit more gains on the table for our athletes, keep them a little healthier, keep them a little happier, and keep them progressing, because we're now allowing our athletes to train with more frequency and more intensity by looking at the tissues that we're training and trying to figure out how to just make them better. So we can use this very well to our advantage and very easily through phase selection, right? So if we're looking at this, what we could look at is look at the way an athlete or the way a client is training and determine what we're going to be trying to get them to use and what the goal of that phase is. If we're trying to build up more resilience or more competence, or like let's go with the example of competence first. If we're looking to train more competence first and we're looking to get them to quote unquote feel the tissues that we're trying to get them to feel more, well, the best way to get people to train to feel things is to train the shortened position of tissues. So if we have somebody who just doesn't have the awareness or the kinesthetic awareness of what they're doing, we might just put them on a bunch of machines and have them train more of the shortened position of movements. If they don't know where their quads are, throw them on a leg extension and give them a couple sets of 10. They will definitely know where their quads are then. Same with leg curls. When they feel those weird things in the back of their legs cramping, they're going to go, oh my God, are those what my hamstrings are supposed to feel like? Right. So we can train this very easily through phase selection, where if we have this client who's very incompetent in movement, we can train them on a lot of machines and give them the ability to really feel the stuff that we're doing without reducing and sacrificing their training effect and output by giving them a bunch of low-level drills. So by giving them this is also going to help to isolate and strengthen up the tissues alone, which we can then use in the next phase to start training more of the lengthened and the mid-range of tissues. Now that they've got a good base of understanding of what their quads are going to feel like, what hamstrings are going to feel like, now if we get them to start squatting and deadlifting a little bit more, we can probably be pretty sure that they're going to have a decent understanding of what those things are. And they're not going to be pointing at their thigh muscles going, oh my God, my knees hurt. They're going to go, oh my God, my quads feel wrecked. Right? So this is going to be an easy thing for us to use to communicate with people. If we're looking at hypertrophy, if we're looking at clients that are hypertrophy clients, that was an example of Gen Pop. Training both the shortened and the lengthened position is going to be very important. The shortened position and the lengthened position of tissues are going to respond very differently to stimulus, and they're also recover at different rates. The shortened position of tissues recovers significantly faster and accrues significantly less mechanical damage than the lengthened position of tissue does. The shortened position of tissues is a much more metabolic muscle range to train. So what does that mean? That means it's going to be accumulating a lot more metabolites and metabolic waste products than the lengthened position will. But the shortened position is also going to be weaker than the lengthened position is. So if we're looking at getting somebody into a more of a strength block, would probably be training more of the lengthened position, which would come with the cost of reduced frequency and potentially reduced intensity over the course of their training cycle. If we're training the shortened position, we can probably up their frequency a little bit because it's going to recover fairly quick, and they're going to be able to get a lot of adaptation out of it pretty fast. So if we're looking at training these, this is an easy thing that we can do through phase selection to see what we can do to make athletes the most successful and allow them to just continue building up more and better. Other factors that are going to influence this are going to be somebody's individual morphology, right? So if we're looking at the proportions and the way that somebody is actually built, this is going to determine more than anything else. And this is one of the things that we look at more in an assessment now than we used to. Before, when we were assessing clients and we were assessing movements, We would look at this through a lens of movement idealism, where we would want to have all of our clients move the same way and basically check off a bunch of predetermined boxes that would say, yes, this is what a squat looks like. When in reality, a good squat and what's going to make a squat is going to look different for every single person, since not everybody is built the same way. So looking at these is going to help us determine both tissue utilization and exercise selection and frequency. If we're using this as our main metric for assessing clients, or one of the most important considerations, likely we will not be able to go wrong because we're looking at that individual first. So we're looking at the length of their limbs, the length of their trunk, all of these things that are going to determine what are going to happen. If there's somebody who's built like me, I'm 6'3" and I have a very, very short torso. So when I'm sitting down, I'm actually shorter than most people who are 5'5". But when I stand up, I'm 6'3". Because my torso is so short, my squat is always going to be relatively hingy. Even though my ankle mobility is fantastic and I can get ass to grass very, very easily, my hips are always going to travel through a greater range of motion than my knees are because they have more room to move. So with this being said, I may have to drop my squat frequency so that I can deadlift a little bit more or with a little bit higher intensity. For somebody who's the opposite, who has very short legs and a very long torso, they may have the exact opposite problem. They may recover super fast from squats and have a very, very quad dominant squat and have a very terrible deadlift. So looking at these two individuals next to each other, would they have to follow the exact same program, or would they go to follow something different? I would hazard they'd have to follow something different. The vector of the load is also going to determine the utilization of the tissue. So load vectors, we have 3 different ones. We have horizontal, we have vertical, and we have diagonal. So a horizontal load vector is going to move both directions. A vertical is going to move both up and down, and a diagonal one is going to move this direction. If we're looking at this is another important thing that's going to determine tissue utilization, because we would have to manipulate our body around the vector to train what we want to train. These are also going to be lining up with we have to make sure that the vector that we're choosing is also going to line up with the line of pull of the actual tissue itself. So when we go through the upper body biomechanics stuff and we look at all of the lines of tissue, if we're choosing an exercise that doesn't follow the lines and we're choosing a load vector that doesn't follow the lines of those tissues, we're probably not going to be training those tissues. And finally, the position of your body is also going to determine the utilization of tissues. If we are arching our bench tremendously hard and we're trying to use this to hit the upper chest or the clavicular head of the pecs, that's not possible in that position. We have to use a different torso position and a different arm path to change the tissues that we're utilizing.